Close your eyes for a second and imagine walking to your kitchen for a glass of water. You just did something no supercomputer on Earth can do efficiently. You didn't calculate a single physics equation. You didn't run a search algorithm through a million possible paths. You just saw it, instantly, effortlessly. And you did it using about 20 watts of power. That's less energy than the light bulb above your head is using right now. Meanwhile, the AI systems we're building to think like us are burning through server farms, guzzling electricity, and still struggling to adapt the moment a goal changes. So here's the question that's been quietly obsessing neuroscientists and AI researchers alike. What is your brain actually doing that makes it so absurdly efficient? And can we teach a machine to do the same thing? A new paper out of Nature Machine Intelligence just got a lot closer to an answer, and honestly, it reads less like computer science and more like a user manual for your own imagination. Researchers zeroed in on 3 mental tools your brain uses every single day without you noticing: cognitive maps, a bit of built-in randomness, and something called compositional coding. Stick with me, this is going to click by the end. Cognitive maps, your brain's GPS for everything. Deep in your hippocampus, specialized cells build an internal map, not just of physical space, but of relationships between ideas, goals, and states. This is the same system that lets a rat learn a maze, and the same system that lets you mentally map out a breakup, a career change, or an argument you're planning to have with your landlord. Here's the clever part. Most AI planning systems, the kind used in reinforcement learning, plan by grinding through massive trial and error. Change the goal, and the whole system often has to relearn from scratch. It's exhausting, and it's expensive. Your brain doesn't do that. Instead, it seems to run something researchers call an inverse model. Rather than obsessively predicting every possible next step, your brain just looks at the gap between where you are and where you want to be and works backward to fill it in. No relearning required. Change the goal and your brain adapts instantly because it was never memorizing steps in the first place. It was mapping relationships. This is, in a very real sense, why you can walk into a totally unfamiliar building and still find the bathroom. You're not running a search algorithm. You're using a map you built for something else entirely and bending it to a new goal on the fly. The power of mental noise. Now here's where it gets genuinely strange and honestly kind of beautiful. The researchers found that the brain doesn't just calculate one clean, optimal path to a goal. It injects randomness, noise, into the process. And instead of that noise causing chaos, it generates a whole spread of imagined possibilities, different routes, different strategies, a mental menu of options, all bubbling up at once. This is what neuroscientists call hippocampal replay, and if you've ever lain in bed running through 5 different versions of a conversation you're dreading tomorrow, or mentally rehearsing 3 ways a job interview could go, you felt this system in action. That's not anxiety being unproductive, that's your brain doing exactly what it evolved to do, stochastically imagining alternate futures so you're not caught off guard by any of them. When researchers built this same principle into an AI model, deliberately adding randomness to its decision-making, the model started generating imagined paths that could route around obstacles it had never encountered before. It wasn't just solving the maze, it was daydreaming its way through it. Here's the part that really separates us from every other animal, though. A rat can imagine its way through a maze, but you can imagine your way through concepts that have no physical shape at all: an argument, a proof, a plot twist, a strategy. To test whether this same brain-inspired model could handle that kind of abstraction, researchers gave it a notoriously brutal puzzle: figure out whether a 2D shape could be built from a specific set of building blocks. This is what's called an NP-hard problem, meaning there's no shortcut, no clean formula, just a genuinely enormous space of possibilities to search through. The model had only been trained on simple 5-block versions of this puzzle. When researchers threw much harder 8-block versions at it, shapes it had never seen before, it figured them out anyway. And it didn't just get there, it outperformed standard reinforcement learning approaches, the current gold standard in AI, doing it with a fraction of the computation. It generalized the same way your brain generalizes when you take a lesson from one relationship and apply it without even meaning to a completely different one. So why should you care about a mouse maze algorithm and a block puzzle test? Because this challenges something we've assumed for years, that real intelligence, the kind that can solve problems it's never seen before, requires massive scale, bigger models, more data, more electricity. This research suggests something almost the opposite. Your brain proves that flexible, creative problem-solving can run on local, efficient, almost biological rules, the same rules powering something researchers are now calling goal-directed imagination, or less formally, fantasy, daydreaming with a purpose. And practically, that means future AI, the kind running on your phone, your smartwatch, tiny efficient chips instead of massive data centers, could start to imagine its way through problems the way you do, not by brute forcing every possibility, but by sketching a map, injecting a little useful randomness, and letting a solution emerge. What strikes me most about this isn't the AI implications, honestly. It's the reminder that the wandering, noisy, seemingly inefficient way your mind drifts through possibilities before landing on an answer, that's not a bug. That's the single most efficient problem-solving system we know of, running quietly behind your eyes right now for the cost of a dim light bulb. If this kind of deep dive into how your brain actually works is your thing, make sure you're subscribed. This is exactly the kind of stuff we dig into every week. And I'm genuinely curious, next time you catch yourself daydreaming through a problem instead of grinding through it, are you going to see it differently? Let me know down in the comments. I'll see you in the next one.